All right, Trent, let's continue. So we saw that with our previous intuitions that building sort of like an increasing stack would help us keep track of what are the rectangles that are constantly sort of extending the previous rectangles. And as soon as we see something that is not bigger or equal to the current element on the stack, then we want to process because if like we see here, as long as it is increasing, they're all extending. But as soon as we find something which is smaller, then sort of that pops this particular element on the stack out because the element towards its left, because it's an increasing stack, would be less, and the element towards its right is also less. So we found that this particular rectangle has come to an end. So to the left and to the right, if they are smaller, then we try to process them. So the same thing happens here. If we are building an increasing stack, then as soon as we find something that is smaller than the top of our stack, then we want to process each of the elements on the stack that are smaller than the current element that we're processing. So let's take a look at it with this example here, where we have 8, 4, 6, 5, 7, 3, and we are given ourselves a dummy sort of here 0, which would help us process this last element in every case. So with that intuition in mind, let's proceed. So we have the first element 8, and that's the only one. So let's push it onto the stack. So we have so let's put the index of that on the stacks rather. So we have pushed 0, right? And then we see 4, right? So 4 is, so the top of the stack is index 0, and 4 is definitely less than what is there on the top of the stack, right? So now we need to process what is there on the stack. So we take that out of the stack because uh, we have seen that towards the left and towards the right, there is nothing towards the left, but there is a smaller towards the right. So we process this. So, and we have seen that once if there is nothing towards either left or right, then we use the right limit, right? So uh, so we use 1 here, which is our right limit, and we calculate what is the area, right? So the area for this guy is 8 times 1, which is the right limit. This is the height, right? And then we pop that out of the stack. So, and then we push the current element, which is fourth index, onto that, right, on top of stack. So this is the top, right now. And then we proceed from there. So then we proceed to 6. So 6 is greater than 4, which is on the top of the stack. So remember, these are indices, right? So 6 is greater than 4, so we push that index on this. So we push index 2, and stack stop is pointing to here, right? So we are building an increasing stack here. And we get 5, and 5 is is less than what is there on the stack currently on index 2, right, which is 6. So we need to process 6 here. And we know that since this is an increasing stack, so the immediate element behind this 2, or on the bottom of 2, would be smaller. And we know that the current element is also smaller. So we know the boundaries for this particular element, right? So what are the boundaries? So for this, first we need to process this. So this is popped out of stack, and then we know that the boundary here is the left boundary is, so the left boundary is 1, and then uh, the right boundary is 3, right? That's the current one that we are at. And so that would be, so right minus left minus 1, which is 3 minus 1 minus 1 is 1, right? And so 6 is, so so that would be 6 times 1, right? So that is height times whatever is the calculation. I kind of messed up here, but you get the intuition, right? 1 times 6, right? So then the current top of the stack is 1, and index 1, and what we are looking at right now is 5, right? So 5 is bigger than 4, right? So we push that on top of stack. So then we push 5, or rather index of that 3 on top of stack, right? So now top of stack is 3, and these are the active elements on stack right now, index 1 and index 3, right? Then we proceed to 7, right? So 4, 5, and now 7, right? So 7 is greater than 5, so that goes, so index of that goes onto stack. So we push that onto stack, so that index is 4, right? So as long as we are increasing, we are good. So 4, 5, 7, which is 1, 3, and 4. 1, 3, and 4. Okay. So then we get to 3, right? So 3 is smaller than what is there on top of stack, right? So index 4 height is 7, right? So now we need to process this guy. So we pop that out of stack, right? 4. So its height is 7, and so its height is 7. But what are the right and the left limits for that? So the immediate element below the current element that we want to process 7 was 3. So so the left is 3, right? So left limit is 3, and the right limit is 5, right? So 5 minus 3 minus 1, which is 1, and times 7, right? So the area would be 7, which matches to what we were processing here for each of them, like 7 times 1 is what we got, and 1 times 7, right? And then we look at the the current top element, whether it is uh, greater than, equal to, or smaller, right? With what we are processing. So 5 is definitely uh, is greater. So 3 is smaller, right? Which is the current element. So it's going to, it's going to trump this out, because we have an increasing stack. So the element below this is smaller, and the element after this is going to be smaller. So it's going to trump this out, right? So now we need to calculate what would be sort of like the units that would be involved in this height, right? So we have our right limit, which is 5, so that is fixed for this. So 5 is the right limit, and we are processing this. So this is out, right? So what is below this? What is below this immediately is this particular index, right? 1, right? So so 5 minus 1, right? And then minus 1, right? So 5 minus 1, which is this guy, right? So we got that. So 5 minus, so this is the interval that we are processing, excluding these, right? Which makes sense, right? So 5 minus 1 is 3, which if you look at this 5 is extending, right? Here all the way, right? So that would be 5 times 3 is 15, right? And you have processed the you processed 5 is out of the stack. So the only thing that is left on the stack is 1, and now you compare that 1 index, whatever is there at 1 index, which is height 4, right? So height 4. So this is processed, this is processed, this is processed. So right now we are processing this. So 3 is still smaller than 4, right? And we know that if we get something to the right which is smaller, then that's going to stop the extension, right? So now we need to process this, and so we pop this out, right? And we know that uh, if there is if there is nothing to the left of the current element, then we use the current index to process the entry as the limit, right? So the height is 4, and our right limit is 5, which is 20, right? So this is the right limit, and this is the height, right? And which matches to what we processed here. And if we draw a line, which gives us the same area, right? 4 times 5, 20. And now there is nothing on the stack, so we push our current element index onto the stack, which is stack top will be just 5, right? Index 5, right? And then we go to our next dummy, which is 0, which is definitely would be smaller than any element in any legitimate element in this sort of like a building stack. So that would pop this guy out. So, and there is nothing on the stack besides this. So we're going to use this right limit that we used previously. So the right limit is 6, and the height is 3, and 6 times 3 is 18. So if you extend this all the way here, right? So you can see you have 6 times 3, 18 as the area, right? And this is what we saw here as well, right? So the largest area that we get here is this 4 times 5, 20. I hope that clarified a few. I kind of realized that I was going a little slower, but I just wanted to make the right intuition and not get confused with too many words or too fast. So let me know if it's slow in your comments, and maybe I can improve that in the next videos. See you till then. Bye.